Howdy, welcome to Computer Graphics Rendering. In this video we're going to talk about Global Illumination. And today we're going to talk about what exactly is Global Illumination, regular expression notation, path tracing versus radiosity, and finally, what are some different techniques out there for doing GI, Global Illumination. So what is Global Illumination? Let's use a scene. Let's just say there's a closed room, a light, the viewer, and an object inside of it that's blocking light. A lot of times in computer graphics, we'll make assumptions, approximations, because we can't possibly trace where every single photon could be going. So in many cases, we might be talking about paths of light that bounce off objects until they get to the viewer, and these kinds of light paths are very simple, but it's the one that's the easiest to calculate, because if you're drawing triangles and shading them, it's the easiest thing to calculate. And this is called local illumination. But what about the other light paths? For example, we know that this side of the box would not be lit. However, in fact, it is lit. So what global illumination essentially is saying, if we were trying to look at, is let's find out where all the illumination could be coming from. And in this particular case, you could have light coming from here, bouncing around the room. The light could be going off this wall, bouncing around. And so what global illumination is determining where all the possible sources of light could be coming from. We want to think about it in terms of photons. So if we think about the rendering equation, then essentially what we want to do is treat all the points around a we'll call this point X on the surface we want to shade. And essentially what we want to say is treat all the incoming directions, or like a hemisphere on top of it, as a source of light. Okay? And we relate how much light is reflected using with the bidirectional reflectance distribution function, or BRDF, which is this element right over here. And this integral represents that hemisphere. In other words, treat all the directions around point X as a potential source of light. This says approximately how much light will be reflected, and this is a recursive definition. In other words, in order to find out what this value is, we might have to trace the ray and then do another hemisphere, and then we might have to trace another ray, do another hemisphere, trace another ray, do another hemisphere, trace another ray. And so sometimes what we'll call this is the ray depth. And sometimes we'll limit paths to one bounce of light or two bounces of light, depending on how much time that we want to spend on this. So we can tell that global illumination is a very hard problem to solve. In fact, it is, in some cases, intractable. You can't really solve it. You can only make your best guess until eventually you get an answer that's hopefully close enough. So one thing that's handy when we're talking about global illumination is to talk about what these different light paths are. And to do that, we use what's called a regular expression notation. Regular expression notation was introduced by Paul Heckbert. So Paul Heckbert introduced this notation in about 1990, and the idea is we use some symbols like E for I and L for light. We also use D for diffuse materials, so like walls, tables, things like that, and S for specular surfaces, so mirrors, metal, shiny objects. And what we can do is we can say, if we have a light path, we can go ahead and categorize it. So, for example, we might say, if we're looking directly at a light, we might say the light path travels from the light to the eye. And if the light path hits a wall first, we might say that the light goes to a diffuse surface and then it hits the eye. Or maybe we're looking inside of a mirror. So then the light path would go from the light to the mirror to the eye. And so when we're talking about a lot of real-time graphics, sometimes we'll say, well, let's talk about a light path to a diffuse surface or a specular surface, and then to the eye. And so a lot of real-time renderers fall into this category. But let's say you want to do one bounce of light. And those light paths might be light from a diffuse or a specular surface to another diffuse or specular surface, and then to the eye. Some renderers, like Radiosity, might only consider more diffuse surfaces. So we might say that they consider light, diffuse surface, and then the eye. Or we might even have a more general case of global illumination, which actually just happens to be light from a diffuse surface or a specular surface. And we use the asterisk symbol to say 0 or more, and then the eye. And then if we're going to completely ignore the case where you only have the light to the eye, then you might say that we have a light source to a diffuse surface or a specular surface. We use the plus to say 1 or more. Okay? And so these essential symbols, which are of course we have E, L, D, and S, but we might have parentheses, or we might have an asterisk, in other words, 0 or more, or we could have a superscript plus. Okay, so this is 1 or more. And so this regular expression notation is very handy at categorizing the different kinds of light paths that a renderer will utilize. So let's compare two algorithms, the path tracing algorithm and the radiosity algorithm, which are both designed to simulate global illumination, two popular techniques. So let's take a look at that real quick. So let's start by talking about path tracing. Essentially, path tracing, we are considering a viewer. So we'll put an eye to represent the viewer. And we're essentially talking about hitting or looking at rays of light that are intersecting other surfaces, and they might be just bouncing light around a room. until eventually we get to some kind of light source. And this is more or less how path tracing is working. The second kind is radiosity. And what we might do with radiosity is we could take our room example. What we want to do is evaluate. We want to evaluate how much light is bouncing from, say, this point to this point. And if there's a light in the room, we're going to time step through and do several iterations where we will say, how much does this patch, and so normally what this involves is subdividing the room into smaller triangles, right? So we might have, or quads is another. We might want to say, of the light on this quad or patch, what is the effect of this patch illuminating this patch? So we'll normally subdivide this into patches, and then we'll check, or we'll simulate light transport between all of the patches. So maybe you want to see this patch to this patch, this patch to this patch, and you can tell this is not extremely efficient, but it actually produces some pretty nice results. So, which is good for, I guess, lower intensity lighting. And then so the two different approaches work well in terms of radiosity. Typically gets smoother results, lower noise than what you would get with path tracing. However, path tracing is more flexible because you can just quickly, if you want to simulate certain kinds of effects. For example, let's say you have a light source and you have a table, and let's just say you have a glass of water. Well, path tracing is really good at getting those little caustics that happen when you refract water and light on a table. So there are some weaknesses to radiosity, some weaknesses to path tracing. Path tracing is even more involved, I think. Well, it's simpler to understand, but at the same time, it takes a long time. You can get noise in your results, so it takes a long time to get a smooth image, whereas radiosity, you can get a nice smooth image, but at the cost of you're limited to the resolution that you break down your scene into these little small patches. But these two techniques are not the only ones used to simulate global illumination. Some are used for real-time rendering, some are used for production rendering. So let's take a look at what some of these techniques are. So there are different ways of applying global illumination techniques. Essentially what we're trying to do is simulate several bounces of light inside of a room. And one popular technique is called photon mapping. And the idea here is, let's estimate what light is doing at various points on the geometry around the scene. And then we can use those. Maybe we want to shoot 1,000 photons. We can use those to help us fill in the gaps in between. And so this is a way of reducing noise, which is can be a big problem with global illumination. So we have photon mapping. It's by Henrik Jensen. And then, of course, there's, okay, well, what about just improving the overall performance of path tracing? So there's a variety of techniques. One's called bidirectional path tracing. Another technique is called multiple importance sampling. And these kind of apply some more advanced Monte Carlo methods to try to reduce the variance in our final images. So one way is just make path tracing better. Another technique is called instant radiosity, and this is for, you can almost do this real time in terms of we want to simulate radiosity, but the way that we do it is by using shadow maps. And by using shadow maps, we can kind of estimate how much light is traveling from patch to patch without actually having to create or subdivide our scene geometry into patches. A related technique to this is called irradiance volumes. And what we do is we calculate light probes throughout the environment we're trying to simulate, and then we use those light probes in real time to determine what the local illumination is at a given point. So sometimes we'll use a Delaunay triangulation to figure out which light probes we got to use to shade a particular light. This is actually a very popular algorithm in real-time graphics nowadays. Another technique is called voxel cone tracing. This is kind of a fairly recent method whereby you simulate the light transport inside a voxelized grid in a scene, and then use cone tracing to trace through the voxels and find out what the global illumination is. So it's like a gather step where you figure out what illumination is going to apply to any given point. And that term scattering and gathering is kind of something that was that you hear a lot with photon mapping, because you're scattering the photons around and then you're gathering the illumination by using those photons as a reference. And voxel cone tracing has some similar ideas where you propagate light through the voxel grid. That's kind of the scattering, and then gather is when you go out and you find out what is the localized global illumination. So those are a variety of techniques for doing global illumination. Definitely worth checking out. So just by way of review, we talked about global illumination, regular expression notation for representing all the different light paths we are interested in talking about, path tracing versus radiosity, the two main techniques for simulating these multiple light paths. And then we also talked about a variety of different global illumination techniques that have been introduced over the years to solve this. So I'd like to thank you for watching the video, and adios.